Thanks very much, Philippe. Thanks everyone for coming. Okay, so back in the early 1990s, when Paul Romer and Philippe were wowing us and amazing us with the insights from endogenous growth theory, Romer would often talk about how ideas are combinations of ingredients or combinations of other ideas. And so, one of his calculations was take a child's chemistry set with 100 different, bottles. How many different, combinations of those bottles can you make? 2 to the 100 more than the number of atoms in the universe. And so Romer thought of this as an argument for why we might not run out of new ideas to try or something, at least not anytime soon. Marty Weitzman, 5 years later, built a beautiful paper around this idea of combinations, that ideas are combinations of other ideas. Interestingly, I won't go into the reasons now since we only have 45 minutes, after Weitzman, combinations were largely forgotten in the growth literature, and they're completely absent from the state-of-the-art models that we write down now. So the first motivation for the paper is, what happened to combinations? Okay, there's a second motivation as well, and this comes from this great paper by Sam Kortum in 1997, which was kind of the precursor to Eaton and Kortum. It's where he first learned about Frechet and Pareto distributions. And so the Kortum paper, which is exactly what my paper builds on, he envisions growth differently from the way Paul and Philippe did. It's kind of a different model of economic growth, obviously very closely related, but his idea is, suppose you've got a hat with balls in it, and you pull out balls, and each ball is an idea. It has a number on it, which is your productivity. And so you pull out a 2, your productivity is 2. You keep pulling, you pull out a 6, your productivity is 6. You pull out a 3, you throw away the 3 and keep the 6. So you only keep the idea with the highest productivity. And Kortum's question was, what assumptions do you need to make on that process in order to get exponential growth in the max? Okay, and it turned out he needed 2 assumptions, the way he set it up. He needed population growth, so the rate at which you draw from the hat has to grow exponentially. So population growth, and that's going to feature in what I'm doing today as well. But he needed a second thing, which is the distribution you're drawing from needed to have a Pareto upper tail. You need to be drawing essentially from a Pareto distribution in order to get exponential growth. And what's sort of weird about that is, well, is the idea distribution for the universe Pareto? Maybe, maybe not. But interestingly, everywhere else we see Pareto distributions in economics, we view it as an outcome rather than assumption. And so, Xavier Gebex made this point a long time ago. So when we see the size distribution of cities being Pareto, so the Zipf's law, or the size distribution of firms being Pareto, Urzo Lutmer's worked on that a lot, or the income distribution or the wealth distribution being Pareto, we now understand those Pareto distributions as the outcome of some process. And it turns out that process is that exponential growth generates Pareto distributions. Okay, so that was something Gebex emphasized. And so it's a little weird to have to assume Pareto distributions to get exponential growth when everywhere else we use exponential growth to get Pareto distributions. So there's a bit of a chicken and egg problem there. But
the Lucas, whatever Lucas model of meeting people was a bit of this kind?
Exactly. So Lucas and Moll, Perla, Tonetti, they build on Kortum. They basically assume Pareto distributions to generate growth, or Frechet distributions, the Pareto upper tail. So the second motivation is, do we really need these Pareto distributions to get growth? So what happened to combinations? Do we need Pareto distributions? It turns out you don't need Pareto distributions, and you use combinations to help you when you don't have Pareto distributions. So the paper makes 2 contributions. The first, which we'll get to just on, very quickly, is just a simple theorem about extreme values. And if you've ever looked at extreme value sort of theorems in statistics, you have these really long, thick books that have all these results, and that there are 3 different versions. It's kind of complicated. It turns out there's a really simple theorem that's underappreciated, I would think. And so I'll show you in a nice way how the max extreme value depends on the number of draws and the shape of the upper tail for kind of any distribution. And then the second contribution is to build a growth model around this. So to do that, let me define combinatorial growth. So exponential growth, we know what it is. Let me define combinatorial growth, because that's not a very precise term. Suppose you've got a cookbook that consists of all the recipes you can make from n ingredients. Okay, n ingredients. How many recipes can you make from n ingredients? Well, each ingredient can be in or out of the recipe, so it's 2 to the n. So you can make 2 to the n recipes from n ingredients. And I'm going to define combinatorial growth to be the number of recipes in a cookbook, 2 to the n, when n is growing exponentially. So much, much faster than exponential growth, kind of explosive growth in some sense. So 2 to the n where n grows exponentially, I'll think of that as population growth, again, like Corbett did. That's going to be my definition of combinatorial growth. What turns out to be true is if you have combinatorial growth in the number of draws, then thin-tailed distributions lead to exponential growth in the max. So like the normal distribution or lots of others, I'll characterize very precisely what the set of distributions is. So you don't need Pareto distributions at all. You just need to draw faster from standard thin-tailed distributions. Okay?
Is the intuition that basically just you're just going to get this explosion in the number of possibilities, essentially?
Yeah, what it is thin-tailed distributions. Think about you're drawing from a normal 0, 1. This is like the great example, right? So suppose you take 100 draws from a normal 0, 1, and your max is, 1.96. Well, it's pretty hard to get, only 2.5% of the time are we going to get a draw bigger than 1.96. Suppose you take 1,000 draws, okay? Maybe you're up to 2.94. It's really hard to get 3 standard deviations above the mean. What if you're 5 standard deviations above the mean? It's almost impossible. You've got to take a lot of draws, an exploding, combinatorially growing number of draws to get the max to grow exponentially. So that's, yeah. Thinner tails means you have to draw faster. That's kind of the insight here. And in fact, I'll show you, you can get exponential growth in the max from any distribution, provided you control the rate at which you draw. Okay. All right, so let me show you the theorem first. And I'll state it here, and then I'll walk through it, the intuition in the next couple of slides. So we're going to take k draws from our hat, and everything's IID, okay? So, and let z sub k denote the biggest value you've gotten from k draws. And we're drawing from some continuous distribution with CDF f of x. And let me define the tail CDF, the complement, 1 minus f of x. Let me call that f bar of x, because since we care about the max, you're marching down the tail. That's where the title of the paper comes from, right? So you're marching down, this normal distribution, CDF. So look at the complement. So f bar of x is decreasing in general, but make it strictly decreasing on its support. So notice I'm making very few assumptions about the distribution. I'm not saying anything about the shape of the tail. Just, we got a CDF that's increasing, a complementary CDF that's decreasing. And then, okay, the max is getting bigger and bigger and bigger the more draws we take. If you want to make things stationary, you have to do something to the max. It's like, in the central limit theorem, hey, you multiply by the square root of n or something. So here, zk is getting bigger. Let's take the f bar transformation of the max. So f bar is decreasing. So now f bar of zk is decreasing. That's falling to 0. If we blow it up by k times f bar of zk, that's some new random variable. That random variable, as k goes to infinity, has a standard exponential distribution. Has a mean of 1, it's stationary. And so what's going on here is the max is growing, but if you take k times f bar of zk, that transformation of the max, that new random variable, is asymptotically stationary with a mean of 1. And so as k increases and the max rises in exactly the right way to stabilize this quantity, k times f bar of zk. It detrends it. Okay? So you can see now how the shape of the tail, this f bar, and the way k increases determines the rise in zk, the rate at which zk is going to increase. Okay. So to think about this, notice this f bar transformation has a nice interpretation. Zk is our max after k draws. F bar of zk is what's the probability that the next draw is bigger than the current max. Right? And that's the thing that's shrinking. When you're 2 standard deviations above the mean for a normal, it's 2.5%. As you're 3 standard deviations above the mean, it's only 1 in 1,000 that you get your next draw bigger. So f bar of zk is some decreasing function. So if we take a bunch more draws, if we increase k to k prime, well, now our max is going to increase on average to some zk prime. More draws means it increases the max, so f bar of zk declines. Well, this is kind of good ideas get harder to find. Inherently in this Kortum approach of drawing balls out of a hat, good ideas, ideas better than the frontier, get increasingly difficult to find. Okay, and that's kind of why you need to take more and more draws. And so f bar of zk is shrinking to 0. If you want something stationary, you need to blow it up, again like the central limit theorem. Instead of the square root of k, you blow it up by k. So k times f bar of zk is the thing that's going to be stationary. And again, the rise of the max is going to detrend this quantity. Okay? So another intuition, and this one's really simple and going to lead directly into the paper. So let me write this theorem. K times f bar of zk is a standard exponential asymptotically. Let me write it this way. So epsilon is the standard exponential with mean 1. And then we add the OP1 to say, okay, this is only an asymptotic result. So now we can do algebra with this expression. So what is f bar of zk? The probability your next draw is bigger than zk is epsilon plus OP of 1 divided by k. Well, epsilon has a mean of 1, so this kind of looks like 1 over k, apart from some noise. Okay? So the probability, for any distribution, the probability your next draw is bigger than the current max is basically 1 over k. All right? And this just is a very well-known result in the theory of record breaking. So suppose we're looking at record high temperatures in Paris, and we only start keeping records on June 1st of this year. Okay? So what's the probability that June 1st is a record? Probability 1, right? We've only got one observation. So what's the probability that June 2nd is a record? Well, if everything's IID, we've now got 2 observations. Either one could be the record high, so it's 1/2. What's probably June 3rd's a record? 1 over 3. What's probably after k days we have a record high? 1 over k. That would be the unconditional probability. Right? Now, if you've observed that June 15th was an especially hot day, well, the probability June 16th is a record is going to be a little different from 1 over 16, and that's what the epsilon is doing there. It's sort of controlling for the fact we might have gotten a little lucky or a little unlucky about our current max. Okay? But, you know, the theorem basically says this applies to the conditional probability. F bar of zk falls like 1 over k for any distribution. And so, here speaking a little loosely, zk rises like f bar inverse of 1 over k for any distribution. All right? And now we can apply that to Kortum's problem. So now pick a distribution, I'll tell you how fast the max grows. Proof, incredibly simple. I'm not going to go through it in the interest of time, but I'm not good at math or statistics, and so if it weren't simple, I wouldn't have, kind of appreciated the point here. It's not completely unknown in the statistics literature, but it's you work through, you look at this 400, 500,000 page book, and this point, it's there if you look for it, but they don't even use it that way. We could talk later about why they don't, but here's some references where if you look hard enough, you can sort of see something like this. But I don't know why it's not like the first page of every book. Okay, let's go to Kortum 97 now. So Kortum says, the simplest version of Kortum is you're drawing ideas from a Pareto distribution. The Pareto distribution, remember, is f of x is 1 minus x to the minus beta. So f bar of x is x to the minus beta, a power function. And power functions are crucial in growth theory, and you'll see that coming up a couple of times today. So f bar of x is x to the minus beta. Apply theorem 1 to that. So k times f bar of zk is epsilon. F bar of zk is zk to the minus beta. I guess I can point a little bit here, right? Zk to the minus beta. And then solve this for zk, right? So I'm just rewriting it, k over zk to the beta. Now invert, zk over k to 1 over beta is epsilon to the negative 1 over beta. Okay? Now, you may know a standard exponential raised to a negative power is a Frechet distribution. So this is where Pareto leads to Frechet. This is the simplest way of seeing it. I don't care about the distribution. This is just some stationary thing. What I care about is to detrend zk, to figure out how fast is zk growing. Well, it's growing at k to the 1 over beta. right? The max grows with k to the 1 over beta. And so now you can see exponential growth in k leads to exponential growth on average in the max. The growth rate of zk, of z, is the growth rate of the number of draws divided by beta. Or the way I like to think about it is the growth rate of the max is the growth rate of the number of draws deflated by kind of the rate at which ideas are becoming harder to find. Right? Beta is how thin is the Pareto tail. A thinner tail means ideas get harder to find, and so it decreases the growth rate. All right, so that's Kortum in a nutshell. Now, pick your favorite distribution, and we can figure out how fast the max grows. So here's one. This is a very well-known result, but just showing you how to use the theorem to get the result, and then we'll get to the growth model. Take the exponential. The normal's a little bit harder because you can't kind of invert it. Take the exponential. So f bar of x, instead of being a power function, is now an exponential function, e to the minus theta x, right? There's our theorem. Plug in zk is e to the minus theta zk. Solve for zk. Now we have to take logs. And zk is 1 over theta times the log of k minus the log of epsilon. The log of a standard exponential is a Gumbel distribution. That's where another sort of standard distribution in the extreme value theory comes from. Again, I don't care about that. What I care about is if you divide both sides by the log of k, zk over the log of k is 1 minus the log of epsilon divided by the log of k. This goes to 0, so now the convergence is convergence in probability. Zk over the log of k converges in probability to a constant. We don't even need a distribution now. And so zk grows with the log of the number of draws. Again, a well-known result. Kortum had that result. It's well-known in the statistics literature. So if you're drawing from a standard exponential, the max grows with the log of the number of draws. And now you can see Kortum's problem. He said, look, if we have population growth in researchers, well, the log of the number of draws is going to grow linearly rather than exponentially, and we're going to get linear growth, arithmetic growth in the max, rather than exponential growth in the max. And that's why Kortum said we need to draw from a Pareto distribution. Okay? The key insight that got me running down this path came from this Acemoglu and Azar paper in Econometrica a couple of years ago, which is, well, just change the growth rate. Assume log of k grows exponentially. And it turns out combinatorial growth is exactly that. Right? So suppose k is 2 to the n, where n grows exponentially. Well, then the log of k is growing exponentially at rate gn, whatever gn is, and now the growth rate of the max is just the growth rate of the log of k, whatever your gn was. So, if you've got a thinner tail, you just need to draw faster. And it turns out for standard thin-tail distributions that we use all the time in economics and statistics, it's sort of this combinatorial thing is going to give you exponential growth. Okay? So that's it for an exponential distribution. Part of the paper is going to be to characterize the set of distributions for which combinatorial growth in draws generates exponential growth. Let me step over now to the growth model version, and I'll give you a slight generalization and show you how the growth model works. So go back to the cookbook. The cookbook analogy is really helpful in this paper. So a cookbook is a collection of K recipes, and what researchers do is they add ingredients to the cookbook, right? At some point in time, researchers have evaluated all the recipes you can make from n ingredients. And again, each ingredient can be in or out, so K is 2 to the n. You know about the sum of the combinations, Pascal's triangle. Okay, so research is learning the productivity of all the new recipes you can make when you add an ingredient to the cookbook. So how are we going to add ingredients to the cookbook? A simple version is this, R is the number of researchers. Suppose each researcher adds alpha ingredients to the cookbook every period. So maybe it takes 1,000 researchers to add one ingredient to the cookbook. Let me forget the 1,000. Suppose each researcher adds one ingredient to the cookbook every period, right? Well, since R is growing with population, N is going to grow with population as well, so we're going to get exponential growth in N. We've got combinatorial growth in the number of recipes, all right? One thing that's going to bother you eventually, if it doesn't already.
Suppose research is input is you use final output for research input. Okay.
That's fine.
Would you need population growth then?
Yeah, I mean it's just like the usual semi-endogenous endogenous growth. If you can use research, and unless there's a the sum of the exponents is precisely equal to 1, you're going to need population growth. But if you've got sum of exponents precisely equal to 1, you don't need population growth. But yeah, so that's, yeah, I'll show you, yeah, so the same stuff that applies in regular endogenous growth theory applies here as well. Notice in the, I won't have time to talk a lot about this point, but
if you have AI like we had in our paper, you would not need exactly like in our paper.
yeah, what you need is the number of draws to grow combinatorially, right? And you can, population growth with 2 to the n is the simplest way to get that, but yeah, you can, exactly. There are going to be other ways to do it as well. I think that's right. The one thing that's going to bother you here, and I'll come back to it at the end, but I want to flag it for you now, is I'm saying, you know, researchers can evaluate all the new recipes that come from adding a new ingredient. Well, suppose we have 4 ingredients. We have corn, tomatoes, onions, and cilantro. We can make 16 recipes from those 4 ingredients. And suppose a researcher adds a new ingredient. We add chocolate for our mole sauce. Right? Now you can make 32 recipes. Every time we add an ingredient, we double the number of recipes. So the researcher has to evaluate the productivity of 16 draws to figure out which one's the best. Okay, fine. But notice, suppose we wait a while and our cookbook has 16,000 recipes in it, and a researcher adds a new ingredient. Now the researcher needs to evaluate 16,000 productivity. You've got to cook all these recipes to figure out which one tastes the best, right? A researcher is evaluating an exponentially growing number of recipes to find the max. And you might be bothered, hey, do researchers really have that superpower? Can they evaluate an ever-increasing number of recipes? You might be bothered. I'll come back to that in a second. But I'm assuming the answer to that question is yes. Okay, but you're right to say, can you really do it? But I think there's a great answer to that question at the end. Okay, so there's a Poisson version that makes some of the math easier. Let me skip that in the interest of time. So here's the economic environment. It's basically a simplified version of Cordum. You know, you've got some continuum of sectors, 0 to 1, CES across those sectors. Each variety is produced with a recipe, and the recipe says to use M ingredients. The M to the minus 1 over rho there is the Benesy thing, killing the love of variety. So I don't want recipes to be inherently more productive because they use more ingredients. Okay, so all the productivity is just the Z in the distribution. So this kills the love of variety here. Each ingredient is produced with 1 unit of labor. For each variety, you pick the best recipe, and this is the Poisson thing just to make all the math work out nicely. Now I'm generalizing. The stuff that's kind of new is in blue here. I'm going to say we're drawing from a Weibull distribution instead of an exponential. What is the Weibull? Just put a beta power on the x. So beta governs, again, how thin is the tail of the Weibull distribution. Okay, and if beta were 1, this would be an exponential. In evaluating ingredients, you know, set lambda equal 1, phi equals 0, that's fine. You can generalize it a little bit. So it could be that, you know, doubling the number of researchers doesn't double because there's some duplication. Adding ingredients could get harder over time or easier over time, according to this as well. So that's just related to things I'd done before, so it works fine here. Cookbook is k equals 2 to the n, that's the number of recipes. And then labor is kind of the only factor here, and so labor has to be used for everything. And there's population growth at rate GL. Okay? Exogenous population growth. All right. So, and then I look at the optimal allocation, or, you know, allocate the L's to maximize Y, and there's a constant fraction of people doing research, and the rest of the people work. So you can do other things here. Again, I'll come back to that, but nothing important there. The number of ingredients grows at an exponential rate, eventually proportional to population growth. So n dot was r to the lambda n to the phi, divide by n dot over n is r to the lambda over n to the 1 minus phi. For this to be constant, this and this grow at the same rate. So the growth rate of n is the growth rate of r times lambda divided by 1 minus phi, and the growth rate of r is just population growth. Okay? So we've got exponential growth in the number of ingredients. A cookbook is 2 to the n, so we've got combinatorial growth here. Yeah, that's what this is. Okay. So now we have to deal with the Weibull distribution. It turns out there's a nice trick that works often when you want to generalize. You could just apply theorem 1 directly if you want to, but there's a nice trick that it's a shortcut. You can, suppose y is exponential, and let y equal x to the beta. Then x is Weibull. But we already know the asymptotics for y, so y grows with the log of k. Plug in, for y, x to the beta grows with the log of k. So x grows with the log of k to the 1 over beta power. Okay? And so the growth rate of the max in that model I just showed you is going to be the growth rate of the log of k divided by beta. The growth rate of the log of k was the growth rate of n, the number of ingredients. The growth rate of the number of ingredients was lambda times population growth over 1 minus phi. And so this is the growth rate for the richer model. Just repeating it here. And so it's a combinatorial march down a Weibull tail in this case. And the growth rate depends on population growth, as in Cordum. It depends on lambda and phi, how researchers evaluate ingredients. Interestingly, you can have phi greater than 0. It can get easier to add ingredients, even though it still becomes harder to get ideas. So beta very much parallels the beta in Cordum. It's how thin is the Weibull tail now, instead of how thin is the Frechet or the Pareto tail. And so beta kind of captures how ideas get increasingly hard to find, and phi can say it can get harder or easier to add ingredients to the cookbook.
Within a paradigm, I mean, you can look at growth as, if you think of GPTs, a succession, a sequence of GPTs, maybe within each GPT you have this. And then when you have a new GPT, when you have a Kuhnian innovation, it's not purely combinatorial. It's a new paradigm.
Yeah.
And again, you start again.
Yeah. No.
See growth as a succession.
It could be a sequence of waves. I agree. It's not obvious here. I think that's an interesting generalization to do here, and it's not totally obvious how to do it, but I think that would be an interesting thing to work on. But I totally agree with you. Yeah, this intuition that, we have steam engines and then we exhaust steam engines, and you invent electricity and then you work through everything with electricity, you exhaust electricity. You invent semiconductors, you invent the Human Genome Project, right? And you kind of figure everything out in that space, and then hopefully there's another space coming. I think that's for sure an interesting thing to think about here. Yeah.
To which extent those big things are themselves recombination or not?
Yeah, exactly. I mean,
maybe they are a bit.
Yeah, it could be. Yeah, the perspective I'm taking here, it'll come back to, there's a slide I'm going to skip, which is, I'm assuming the distribution doesn't shift over time, right? You're just drawing from the same distribution always. So the ancient Greeks were drawing from the same distribution we are now. Is that good or bad? You can allow it to shift if you really want to. So Cordum had a way to let it shift. I can make it shift in the same way. I think there's actually, yeah, let me not say what I was going to say. I'll save it for a question. Yeah, that's the thing I'm skipping now. Yeah, new ideas are future ingredients. I think it's interesting to think about it not shifting. You basically have to discover electricity, radio, and semiconductors before you get to the smartphone. So there's a natural order to things. Yeah, anyway. Okay, for what distributions do combinatorial draws lead to exponential growth? Let's look at the set of distributions that work, quote unquote, and the ones that don't work, and think about what that set looks like. So here's the theorem that gives you the result. So take the growth model I just showed you, but now let z be drawn from some general f of z. And it's unbounded. If you want exponential growth, you need unbounded. And it's monotone and differentiable. So we need to take derivatives now. And let eta of x be the elasticity of the tail CDF. So eta of x is d log f bar d log x, with a negative, because f bar is decreasing. So eta of x is positive now. So it's the elasticity of the tail CDF. Then here's the result, if and only if. The growth rate of productivity is asymptotically constant at a rate that's the growth rate of ingredients deflated by some alpha. If and only if the elasticity of the tail CDF is asymptotically a power function with power alpha. Okay? So I'll show you some comments about that. So Thinner tails require faster draws, but still require power functions. Power functions, I said, are crucial to growth. It's just now the power functions in the elasticity itself rather than in the function, the tail CDF. So some examples, the Weibull distribution, the F bar is e to the minus x to the beta. So the elasticity of the tail CDF is exactly x to the beta. That's why the Weibull is kind of the canonical example for combinatorial growth. It's not an asymptotic result that you have the constant elasticity. It's just there. The normal distribution, f bar of x is 1 minus the integral of e to the minus u squared. Notice e to the minus u squared looks a lot like e to the minus x to the beta. The normal, you can't use the existing tricks don't work so well because you can't invert that f bar. It doesn't have a closed form, but you can use that theorem I just showed you to see that the elasticity of the tail CDF for a normal is asymptotically x squared. And so the key alpha parameter is 2, just like the Weibull with beta equals 2. Okay? Another intuition, go back to Cordum 97, f bar of x was itself a power function, x to the minus beta, and so the elasticity of the tail CDF is just a constant. And what we saw is that exponential growth in the number of draws is enough. Well, here, the tail CDF is the exponential of a power function. It's exponentially thinner than a power function. And so you have to march down it exponentially faster. Exponentially thinner, march down it exponentially faster. Notice there's nothing crucial here about the 2. That's just helpful for the combinatorics. But e to the nt, or 37 e to the nt would work just fine here. The 2 doesn't play a crucial role. It's just exponentially thinner means march down it exponentially faster. Now you can see how, with any distribution, you can figure out, you can reverse engineer how fast we have to draw if you wanted to get exponential growth. So when is that tail elasticity asymptotically a power function? Well, the normal, the exponential, the Weibull, the Gumbel, the gamma logistic, other things, generalize the Weibull. X to the alpha, e to the minus x to the beta, or e to the minus polynomial. The highest order of the polynomial is going to be the key alpha parameter that determines how thin the tail is. So it's distributions where the tail is dominated by the exponential of a power function. More interesting, I think, is when does it not work? So a surprising thing at first, but when you see it, it totally makes sense, is that combinatorial draws from a log normal distribution, that's another very common thin-tailed distribution, that will not generate exponential growth. Why not? Well, I told you it works for a normal, right? So when you draw from a normal, combinatorial growth generates exponential growth in the max. Well, if the log of x is normal, now you're saying percentage increments are normal. Well, that's going to be too thick, right? You can't go back and forth between percents and units in growth. It only works one way. Another way so that tail will be too thick and you'll get explosive growth. Another way to see it, suppose the log of x is exponential. If the log of x is exponential, then x is Pareto. So if it works for the exponential, it's not going to work for the log exponential. And we saw it doesn't work for the Pareto, you'd get explosive growth again. That tail is too thick. There's an interesting thing related to extreme value theory that I won't go through here. So here's, if you want, how does the max behave for lots of distributions? Here are the ones I've shown you already. Here's the log normal. It's e to the square root log k. The Gompertz for demographics, it grows with the log of k. There's a connection to Romer here that, I gotta skip. Let me skip that. Okay, so at this point in the paper, you may be wondering, and I was certainly wondering, okay, this is fun math, but are we just playing math games? And maybe it's all equivalent somehow. It turns out no, and that's why I was really happy to realize this part of the paper. So let's look at the data. And what I'm going to show you is you don't even need fancy econometrics. Your eye does enough of the trick. The data very, very much favors the combinatorial model over the Pareto model. Okay, let me try to make that case now. So Cordum was designed to match a key fact in the data. And I'm going to put fact in quotes. I'll show you the fact in a second. His fact, which is an amazing fact if you've ever seen it, is that the number of patents granted by the U.S. Patent Office in 1915, 1950, and 1980, it's 40,000. It's a constant. So Kortum wanted a model where a constant number of patents, a constant number of good new ideas could generate exponential growth. And this is very much micro-foundations for Aghion and Howitt in some sense, that ideas on average are proportional improvements. So if ideas are proportional improvements, then a constant number of new ideas gives you exponential growth. And that's what Kortum saw in the data, and that's Pareto distributions make ideas on average proportional improvements. The ideas are big, and so a constant number of new ideas generates exponential growth. Okay, so how did he map patents into the model? So go back to the theory of record breaking. Remember I told you that if you've got k draws, what's the probability that the next draw exceeds the frontier? 1 over k. So Kortum said, we're going to let things be patented only if they exceed the frontier. So when you've got a max, only the fraction 1 over k of your new ideas are going to exceed the frontier and be patents. And so their k dot, dk dt is the number of recipes we're adding to the cookbook. The fraction 1 over k of those are going to be exceeding the frontier. Those are going to be patents. So the flow of patents in the model, this was Kortum's approach, is k dot over k. K dot over k, if k is growing exponentially, was a constant, right? So that's how Kortum gets a constant flow of patents in his setup. You know, again, ideas are big, so a constant number of new ideas generates exponential growth. What about here? So go back to the, alpha r, the lambda 1 phi 0 case. So k is 2 to the n. K dot over k is the log of 2 times dn dt. dn dt is just the alpha times the r. So k dot over k grows with the number of researchers. So in the combinatorial model, the flow of new patents is rising exponentially with population growth, for example. Right? Researchers is rising, so number of new patents is rising. So the interesting thing is that the combinatorial model predicts that the number of patents granted by the US Patent Office should be rising exponentially. The Kortum model with Pareto predicts the number of patents granted by the US Patent Office should be a constant. Okay? And what it is that in Kortum, ideas are big, as I just told you, so a constant number generates exponential growth. Think about drawing from a normal distribution. Ideas are small. If you happen to get an idea that's 5 standard deviations above suppose our max is 5, if you happen to get an idea that's more than 5 standard deviations above the mean, it's likely only tiny amount above. If you want exponential growth, you want to be 5% above the max, well, you need a lot of draws out here to be 5%. So you need a lot of new ideas to get the max to be 5% better than the frontier. So when ideas are small, it takes a growing number of them to generate exponential growth. And so what does the patent data look like? Well, so Kortum was looking at the green line, patents granted to US inventors, and he was sort of stopping right here because he was writing in the early 90s. And so, yeah, you could cherry pick your dates and say this is constant, but notice 2 things. First, even his number looks like it's growing now. And second, this was never the right number to look at. The number of ideas relevant for US growth is the number granted to all inventors, not just to US inventors. When Toyota or anyone else patents in the US, those ideas are relevant. And so the question, the test of the model is, does the blue line look like a constant or like something growing exponentially? And of course, it's growing like crazy. Now, this is not totally dispositive because, as Josh has told us, there's all these changes in patent laws. It's not clear a patent today is the same as a patent in the past. So, it's not an econometrics question, it's a data question.
The Chinese patent examiner has to carry a lot of weight to make that true. For you to think about a patent equals an idea.
No, this is only granted by the US patent
We
office.
don't blame the Chinese for this.
Yeah, this is
There's lots of things we blame the Chinese for, not this.
yeah.
We can still blame Chinese, but part of this that's globalization. I mean, you might not legally
But
say
still,
the US.
No, but if those are good ideas, then
10%
they're good
of
ideas.
this is global. That's
Oh, as that theory.
We know how the sausage is made, right?
So here's the Amit Seru, Kelly et al. Breakthrough patents. So does this look constant or growing? I mean, it's gone from 800 to 25,000, right? So that doesn't look constant. Here's by technology class before 1990 to avoid the software algorithms. All these, almost every class is growing exponentially. The only ones that are declining are leather pelts or whatever.
I'm very concerned about our competitiveness
Yeah, exactly. Here's academic articles growing exponentially. So I don't want to claim the evidence is decisive. It's not a question of econometrics. It's a question of you tell me what the time series for ideas is, and let's measure it. Is it constant or is it rising exponentially? That's what we need to do, and we don't have great measures of ideas.
Yeah, no, it's decisive that it's growing. What's not decisive is whether that really represents a true growth in ideas.
Exactly. No, I mean the true idea series is that growing. That's what we need. Absolutely. Okay. So let me finish with two quick remarks. Good. So first, remember I said, is it plausible that one researcher can evaluate the recipes, the productivities, from an exponentially growing number of recipes? You might be worried that we're asking too much of our researchers. And what you can realize now is that, well, maybe it's only the good ideas that take time to evaluate. Okay? So how many good ideas are there per researcher? Well, let's go back here. Remember, the number of good ideas grows with the number of researchers in this case. So with phi equals 0, the number of good ideas per researcher is actually constant. So, when Romer was presenting these combinatorial calculations, the chemistry set example, he gave a talk at Berkeley, and George Akerlof was in the audience, and Romer was saying, yeah, we got billions and billions exponentially growing numbers of ideas. George said, well, how many of them are chicken ice cream? And the point is that most of the combinations are totally useless. Well, that can help us here because the researchers don't need to focus on the chicken ice cream. They throw that out immediately and focus only on the good ideas. Those are the ones that take time. And good ideas per researcher can be constant.
The Howitt model, the 99, it was the idea that you could spread and you could go up and you could go so he said, maybe you have many perfumes, so that doesn't count. And what counts is a similar idea.
Yeah, that's related to your GPT comment.
Also, Aghion had a similar model in
Yep.
1998.
Yep.
So he said, suppose that only those that go vertical matter, maybe there are many horizontal replications that don't matter. And you still...
Yeah, that's kind of the opposite of your GPT point, remember? Because this point is saying it's only the vertical stuff that matters and the horizontal doesn't. So the steam engine, we're getting better and better at the steam engine, but adding electricity less important. So there's a tension there.
That's where input to what?
Yeah, there's a tension. So let me give you another. So chess players, right? This is another kind of explosive problem. Chess players find the best move, among an exploding list of things. And Henri Poincaré, Matt Clancy pointed me to a great quote. Poincaré says, what about mathematicians proving theorems? He uses the word combinatorics. He says there's a combinatorially set of theorems we could prove, but we don't waste any time on the bad ones. We focus on the good ones automatically. And so it's exactly this point. So I'm not claiming this is an answer to this question, but at least it's one answer. Okay, then the last thing, this is actually quite important. So what are some you could call them bugs or features of the approach I've shown you. So basically, one thing I want to say is wherever Pareto's been assumed in the literature, maybe you can use thin tails now. So the Lucas Moll, Perlo-Tedeschi technology diffusion, trade models, search models, productivity. So a beautiful feature of Corda that is going to be lost here is that one assumption, this Pareto distribution, gave you a theory of growth, but it also gave you a theory of heterogeneous markups. Markups are proportional because ideas are proportional, and a theory of the heterogeneity of productivity of firms in the cross-section. So one assumption gave us three things, and that's just really, really great, and that's partly why this Corda approach has spread to so many literatures. If ideas are small, you lose this beauty in these connections. Combinatorics gives us the theory of growth. So we've got the first thing, but because ideas are small, the markups and the heterogeneity disappears. You can't use the same, you get to charge a markup based on how far ahead you are of the next person. Because now the next person is right behind you. Because ideas are small, everyone's close together. And so cross-sectional heterogeneity, it's going to disappear. Cross-sectional markups, if they were driven by productivity differences, would disappear. The gaps between ideas are too small. And so this is either a bug or a feature. Let me give you the feature. Maybe. So we relied on this Pareto assumption because it was great for growth and it gave us other things. So three things for one assumption. That's good. What I think is possible, maybe this was the wrong assumption. And so it didn't give us the theory of growth. And so now the combinatorics gives us the theory of growth, but now we need a new theory of markups and firm heterogeneity, and that's, you know, that's something we need to think about. And, you know, there's some ideas there.
So what he does is not done going this way.
You can't, I think you could say that, you know, some you know, I'm the frontier, and John is just epsilon behind me, and Josh is a little bit further. You know, and what we just say, I say, look, if anyone tries to enter, I undercut you, and so none of you guys enter, and that allows me to charge a markup that's not based on me to John, but, you know, the person 10% behind me. That would do it, but that's not the standard way we do it in this literature. So you need a different story, but that's an interesting thing to think about. All right, well, I'm done now. Happy to take more questions.